All right, so we have a couple of warm-up questions regarding motion maps. You should recognize these images because they were in the reading that you guys were assigned yesterday that went along with your homework last night. So I'm hoping that you completed that homework assignment either in class yesterday, or if you weren't able to finish it in class, whenever you got home, it was just that 5-question Google form, and it was about motion maps that look like this one. It says, use the image to answer the questions. Number 1 says, examine the picture above. Which car is moving faster? And then number 2 says, how do you know? So let's see. Ife, which one is moving faster, A or B? B. And how do you know that?
The arrows are longer and it's traveling at the same distance.
Yep.
Less time.
Yeah, the arrows are longer and it traveled the same distance in less time. Perfect. Okay. Something like that is what you guys should have typed out in that assignment for this question. Okay. Any questions about the warm-up or motion maps in general? All right. Hopefully not, because that should have been ideally pretty straightforward. We're going to add to that today with some notes on distance and displacement. You guys do have an assignment tonight in My Open Math. Some of you may have started it yesterday, which is perfectly fine if you did. I didn't tell you to do it because you had another assignment, but I know that some people actually did open it up and get started. That assignment in My Open Math will be due tonight by 11:59 p.m. So you will have hopefully some time in class today, and then whatever you're not finished with, you can finish at home.
How many questions are there?
I don't remember off the top of my head. I'll have to check. So this one says, fill in a data table from the information in the motion map. So looking at a motion map, you should be able to gather how much time has passed and what your position is at each of these subsequent seconds. So with this one, we're starting at a position of 0. I know that because the arrows are all pointing to the right, and this is the first dot that I see. And so I would say that I start there at a time of 0, position of 0. And after 1 second, I would be at this position right here, halfway between 5 and 10. Okay, because each of these arrows is going to represent 1 second unless I tell you otherwise, which means after 1 second, we'd be at 7.5 meters. After 2 seconds, we'd go from that position to 15 meters. A third second would take us halfway between 20 and 25, so to 22.5 meters. And then all the way to 30 meters after 4 seconds. And if I counted the arrows, I would have already known that this is going to be 4 seconds of motion. Okay, but we're getting the numbers from that number line. So now we have 2 different things we can look at to help us answer these questions. I have 2 questions for you. Number 1 says, how far does the car travel from 0 to 1 second? And number 2 says, how does the distance the car travels from 3 seconds to 4 seconds compare? So comparing 0 to 1 to 3 to 4, how does the distance that you're traveling compare? I want you to discuss this with your neighbors. You have 32 seconds, and then I'm going to call on somebody to share. If I haven't called on you yet, you're definitely fair game because I've been highlighting. All right, we'll start with number 1. How far does the car travel from 0 to 1 second? Aya.
7.5.
Yeah, 7.5 meters. Perfect. Okay, you can get that from either the diagram or from the data table. Number 2, how does the distance that it travels from 3 seconds to 4 seconds compare? So we just said it travels 7.5 meters in the first second. So I'm asking you, how does the distance it travels between 3 and 4 compare to that? Addison.
7.5.
Yeah, it's the same. It's 7.5 meters as well. Each second that passes, this car is traveling 7.5 meters. And if you're traveling the same distance each second, we would say that this car is traveling with a constant velocity. Okay, and that's what we're doing in this unit, is objects moving with constant velocity. Another way to represent motion, so beyond data tables and motion maps, we're also going to use position time graphs, which we will also call XT graphs. In physics, we use the variable x for position. If I ask you what position you're at, you could say x equals whatever. And then t for time. And so you'll hear me say xt graph or position time graph. But another way to represent motion is with an xt graph. This graph plots time, usually in seconds, but you could have other units, on the x-axis, and position, again, usually in meters, but you could have other units on the y-axis. And so you'll have those two variables plotted against one another. And this graph, just like a motion map, can reveal the position of an object at various times in its motion, and you can see very visibly when no motion occurs. So it's similar to a motion map. It can show that one-dimensional motion. It can show when you're moving. It can show when you're stopped. It's just, of course, looks a little different because it's a different type of representation. Whenever we are working with position time graphs, and with any graph in physics, the slope of the line is going to give us some information about the information in that graph. And we've talked about this before. You guys did have to do a line with your spaghetti bridge lab, and the slope in that mattered. We talked about it when we did notes on graphs. The slope of those lines matters. It means something. And so if we look at this graph, we're going to talk about what that slope might mean. Okay, so this particular graph doesn't have a slope. It's a slope of 0. It says, what can you tell me about this object's motion? What happens to its position after 1 second? Take a look at that graph and tell me, or talk to your group first, about what this object is doing. What is its position doing each second? Okay, you have 19 seconds to discuss with your neighbors. Probably too much time for that one. That was pretty easy, but it's almost done. Okay. Hopefully, if you weren't sure, your neighbor was. Kennedy, what can you tell me about this object? What is it doing? What happens to its motion after 1 second, or its position after 1 second? Sorry? Yeah, it stays the same. It's still. It's not moving. Okay, if your position is 6 meters, 6 meters, 6 meters, 6 meters. If you're at 6 meters the entire time, you're not going anywhere. So if you see a horizontal line on one of these position time graphs, then you would say that object is stationary. So our motion map, we had dots. Okay, on this, you're going to see a slope of 0 or a horizontal line. Because that horizontal line means that that object is staying at the same position as time passes, and if it's not going anywhere as time passes, then it's not moving. You would say its velocity is 0. What about this graph? Take a look at its motion each second. Okay, again, turn and talk to your neighbors and see if you can figure out what this object is doing each second of its motion. It's probably more time than y'all need. All right, what do you think, Christopher?
It's moving at 2 meters each second.
Yeah, it's moving 2 meters each second. Is that what you said? I couldn't hear you. Yeah, okay, it's moving 2 meters each second. Okay, if you look at this line and you look at 1 second, it's at 2. At 2 seconds, it's at 4. At 3 seconds, it's at 6, and so on and so forth. Okay, and so this object is moving with a speed of 2 meters every second, or 2 meters per second is how you would read that. Okay, does this object change direction and start moving backwards at any time in its motion? And then second question might give away the first. What might that look like? Okay, so again, talk to your neighbor if you're not sure. I think I'll give you less time than this says because I feel like y'all don't need that much for this. You have 14 seconds. All right, Zachary, does this object go backwards at any point?
No.
No. What do you think that would look like if it did?
It would be... It would go down and go here and then it would come down.
Yeah, it would go down. You'd have a negative slope. It'd go back toward the position of 0. It would look something like this. Okay, now it might be that it went forward and then backwards, or if an object just went backward the whole time, it would look like that. Okay, so again, the slope matters. If you have a positive slope, you're moving forward. If you have a negative slope, you're moving backwards. Okay, as we already determined, this object moves at a speed of 2 meters per second. If the object was twice as fast, how would its displacement differ each second? If you go 2 times as fast, what's going to happen to your position each second of motion? Okay, what do you think, Joshua? You are going to go faster, but each second, how would your distance traveled compare? It'd be doubled, yeah. If you're going twice as fast, then instead of traveling 2 meters in a second, you'd travel 4 meters in a second. Okay, and so if you went twice as fast, your slope would be twice as steep. This line right here represents 4 meters each second. So again, slope matters. Positive slopes forward, negative slopes backward. And then if your slope gets steeper, then you're moving faster. If it's more shallow or flatter, then you're moving slower. Okay, so that's a summary of what we just looked at with these graphs. You might want to jot these things down if you haven't already written them out. But the slope of the line tells us a lot about an object's motion when we look at an xt graph. So on a position time graph, a slope of 0, that's going to be your horizontal line, means the object isn't moving. A positive slope means you're moving forward. A negative slope means you're moving backwards. And then if you look at the steepness of the slope, the steeper the slope is, the faster the object is moving. The more shallow the slope is, the slower the object is moving. And again, you can relate it back to those numbers that we looked at as well. If you're going 4 meters per second instead of 2 meters per second, your line has to have a steeper slope. In fact, the slope of the line in that case is 4, because you're going 4 meters each second. That's what the slope is. Rise over run. Okay, so again, slope on a lot of these graphs is going to mean something. So back to the first image that we looked at. By the way, if I go too fast, you guys can open this on your own screen if you want. That was slide 97. All right, so back to the question we started with. It says, draw a graph showing the same motion. So we have a motion map. We have a data table. Now we're going to plot the points on an xt graph, starting at 0, 0. After 1 second, we're going to go to 7.5, which is about right here. After 2 seconds to 15. After 3 seconds to 22.5. And after 4 seconds to 30. And we're going to have a straight line because we're moving at a constant speed. Each second that passes, we're moving 7.5 meters. And so the slope of my line is 7.5 meters per second. Okay, and it is moving forward, so my slope is positive. So that's kind of taking everything we just talked about and putting it to use here. You guys will have to be able to match up tables, motion maps, and graphs, so you need to be able to do what I just did as well. You can jot this one down as an example if you like. We can also use position time graphs to determine an object's distance traveled or its displacement. There's a lot of questions I can ask you from a graph like this. Okay, but I'm going to ask you these two. What is the total displacement shown and what is the total distance? Okay, well, I can tell you this right now. Does this object ever go backwards? No. Well, guess what? I talked about this the other day. If all you do is go forward in a straight line, your distance and your displacement will have the same magnitude, the same number value. They're only different if you go backwards or if you turn or something like that. In this case, everything's going to be linear. We're only doing one-dimensional motion. Okay, and so in this case, they're going to be the same. But my displacement is how far I am from where I started. So all you have to do is look, where did I start? I started at a position of 0. Where did I end? I ended at a position of 25. And so my displacement is 25 meters forward from where I started. Again, displacement needs a direction. So I'm going to label it as positive 25 meters. Or you can put 25 meters forward, or if I had written a scenario above it that said he's moving east or something, you can use that. Okay, the total distance, I don't need a sign for that one. It's a scalar quantity, so just 25 meters. It doesn't matter which way it was. If the displacement had been negative 25, the distance would still be 25 meters. We don't put a sign on it. Okay, but again, sometimes they're more tricky than that one because that one was only forward. When they go backwards on themselves, then you're obviously going to have different values. Here's how you tell distance and displacement on an xt graph. Distance is the total sum of all forward motion and all backward motion. Again, I don't care which way it is. If I moved, I'm going to add it up all together. Displacement, on the other hand, is how far you end from where you started. So if you backtrack on yourself, that is subtracting from your forward motion. Those are going to cancel each other out, at least partially. Okay, if you end at the same position where you started, your displacement will be 0, just like we talked about yesterday. So let's look at this graph. Okay, here is a different position time graph. Okay, again, same two questions. What is my total displacement? What is my total distance? I would like you guys to look at this one and discuss it with your neighbors and see if you can figure out how you would answer these two questions. You have 31 seconds to discuss, and then I'm going to call on somebody to share their answer. All right, Rylan, total displacement. Yep, what is my total displacement in this graph? Perfect, negative 40 meters. The negative tells me my direction, okay, and 40 is the magnitude, and I know that because I started at 0 and I ended down here. The time is 50 seconds. That's not what I'm looking at, though. I'm looking at the position I ended, which is negative 40. Okay, so my displacement, if I go from 0 to negative 40, again, I took a really roundabout way to get there, but that's where I ended up. That's how you find displacement. Displacement's a lot easier to find, honestly, than distance on these things, because distance you're about to have to add everything up. But yes, that one's negative 40. Okay, my total distance, thank you, Rylan. My total distance, Megan.
160 meters.
Okay, so let's check, because I honestly don't remember. Okay, so we go forward 60. And then we go backwards from 60 to 0, that's 60 more, so that's 120, and then 40 more all the way back behind where we started. Okay, so 120 plus that 40 more is 160. Okay, good job. Okay, so that would be your total distance. Again, any questions about how to read that? Okay, I'm hoping y'all are like, that's really easy because you're about to do a bunch of it. Okay, if you haven't already done so, go ahead and head to myopenmath.com, or you can go to Schoology and click the link that will take you there. The assignment that you are working on for the remainder of your class period, which is 26 minutes, is the assignment 106, Distance and Displacement Problem Set. You have until the end of the period, obviously, to work on this. If you're not finished after that time, then it will be homework. It is due by 11:59 p.m. tonight. The unit summary, I said it's posted. It's not. That's from last year. I am going to be posting the unit summary. I mentioned it to you yesterday, but what I need to do is I need to get all of the physics team student rosters, and I need to put all the names in there because the unit summary actually pulls your ID and randomizes numbers for you, so it's not the same as your neighbor. So I need to get that done. So that should be ready by Thursday of this week. So it's not there yet. It is just a bunch of practice, and it will be a redo for a daily grade. It is also a good test review. And last year, for some of the units anyway, we chose to also count it as bonus points on the test. So that is a discussion I'll be having with the physics team today to see whether or not we want to do that again. But this is not there yet, so ignore that. What you need to do right now is 106, Distance and Displacement Problem Set. If you have questions as you're working, please let me know.